we present GaussianHeads, an end-to-end learning of drivable Gaussian head avatars from coarse-to-fine representations.
Our drivable approach takes a driving video as input and produces high-quality human head avatars that can render in real time. In our approach, we use a multi-view RGB triplet input to generate local animation codes and global transformation parameters. We then use a vertex deformer to generate deformations on top of a template mesh in a base pose. And the resulting deformed mesh is posed to the world space using global transformation parameters. We initialize the Gaussians on top of the posed mesh by uniformly sampling positions on the UV map. The Gaussian properties are then refined through taking a fine step. For this, a Gaussian offset decoder that takes the animation code as input is employed. We then predict the Gaussian color and opacity values by employing separate 2D CNN decoders, and splat the Gaussians onto the image plane, resulting in a photorealistic rendering. We now show the driving results achieved by our approach on expressions exhibiting large facial deformations. We also show driving results for talking sequences.
This evidence. So he's actually decided to make his own way and release himself by doing.
And a lot crazier. And then you also have Joe Pritchard's son, who is a queer man, and he's living with his husband, and they adopt a child from Vietnam, and it's.
We show novel view synthesis results of our approach on challenging sequences with a moving head.
Other dudes, and you know what, like in Germany average height is like 180 something centimeter, and I'm just 177, and the opponent of mine are like bulky, muscular, and way taller than me, like close to 100 kilogram weight. So if you do the I'm 70 kilogram weight, and if you do the sparring with those people,
we visualize the disentangled learning of the local animation codes and global transformation parameters. We now show comparisons of our method against the related approaches. In this example, notice how the competing approaches struggle with the topological changes, such as the tongue coming out from inside the mouth. We also show detailed fine strand hair reconstructions in comparison to the related approaches. Also note the temporal stability of our results. Our model produces sharper results for facial hair in comparison to the related methods. Our model also reconstructs the dental region with higher fidelity in comparison to the related methods. We show an ablative analysis of the core components employed by our approach. Without coarse deformations, our model struggles to produce details in facial structure undergoing strong motion. Without fine deformations, our model fails to reproduce the fine-level details in structures such as the teeth. And without employing a temporal loss term, our model produces artifacts in regions undergoing strong motion changes. Without employing a landmark alignment loss, our model misaligns expressions, leading to loss of details inside the mouth interior. We observed that the perceptual loss helps with overall sharper results, and using a vertex loss on the vertices of the deformed mesh helps with accurate expression alignment. We show an application of our method. The application demonstrates driving our model using a parametric face tracker. We rasterize the mesh renderings of the parametric face tracker onto the image plane and use the mesh rasters to drive our model. Thank you for watching. Here is another high-quality result produced by our method.